Boa tarde, pessoal. Good afternoon, guys. Today, Matheus will talk about the multi-messenger detection of black holes binaries in dark matter spikes. It is a recent paper he will discuss with us. So, let's begin.
Hello, everyone. Let me just put here. All right. It's not good, yeah? I think that... It's good? The people in the meet can hear me well? Do you test the mic? Yes. Okay. So, good afternoon, everyone. Sorry. Where is? Okay. All right. Everyone is here now. All right. So today I'm going to talk about a recent paper that I really think is a really interesting paper that came out those days in the archive. And it's about a multi-messenger detection of black hole binaries in dark matter spikes. So the basic idea of these multi-messengers is to use some kind of gravitational waves source together with some luminous source like gamma ray source and put bounds on dark matter. For example, we can put bounds on the Hubble constant, and here this specific paper address some limits they want to put in dark matter through these multi-messenger detections, right? So the basic idea is to use the gravitational waves in spiraling, generated by binary black holes, that will be detected by the LISA. The next space, LISA is laser interferometry space antenna that they will send to the space, and will use this space interferometer in order to observe some frequency range that we cannot observe in the space ground interferometers those days. Basically, if I'm not wrong, the space ground interferometers, there is some frequency range that goes to 10 hertz to 10 to the 4 hertz, if I'm not wrong. And while the LISA, the frequency range of LISA is going to be in the scale of the millihertz. So it's really interesting to study, for example, the spiraling mergers or regarding the supermassive black holes. So people want to use supermassive black holes, and especially with something we call of extremely mass ratio. That's some supermassive black hole and a stellar compact object, stellar mass compact object that will spiral and goes in the direction of the black hole, the supermassive black hole, generating a LISA, a gravitational wave that can be captured by LISA, right? And the idea is to study this phenomenon together with dark matter, because since in the galaxy we have dark matter in the galaxy given by some density profile of Navarre-Frank-White type profile, we can use these profiles in order to study the luminous signal, gamma ray signal that dark matter can possibly emit, for example. So basically, it's I will show here the idea of the paper, but just in advance, we will have this spiraling gravitational wave signal will influence the gamma ray flux coming from dark matter annihilation, and the spike self-annihilation can decrease the luminosity from 10 to the 90% of its initial value. So it's more a proof of concept that we can do that with LISA, and this is a short letter of a full version paper that probably will come later on archive. That's not a lot of the details of how they do that. It's just more a proof of the concept that they can use LISA in order to put some bounds on dark matter spikes, right? On the dark matter annihilation. So basically, he starts talking just initially about LISA, that the primary targets of LISA are basically the coalescence, the spiral and coalescence of supermassive black hole binaries. And the more, like I said, the most promising sources are the extreme mass ratio in spirals. That's basically a stellar mass compact object that gradually spirals into a supermassive black hole, okay? And the idea is that the supermassive black holes, if they grow adiabatically, they grow very slowly, they will have a cusp dark matter type profile. It's a different of a usually Navarro-Frank-White type profile, but it's the Navarro-Frank-White type profile. When you compute some limits, you can see that it goes as a 1 over r, which r is the diameter distance of the center of the galaxy in the nearby vicinity of the center, and goes with 1 to the r to the cube in the very far regions of the galaxy. So the cusp galaxies are more sharper density profiles than the Navarro-Frank-White profile, and they usually fits very well with the supermassive black holes. So we have a profile of the type 1, a density profile that goes with 1 over r to the gamma. Gamma is a coefficient that depends on the supermassive black hole, on the type of the dynamics of the galaxy. And generally, this gamma goes from 1.5 to 2.5. All right, so it's a different type of profile, but it's really interesting because we have this cusp profile here, and since the supermassive black holes grows adiabatically, we will have this cusp profile, and there's a lot of dark matter in the nearby regions of the supermassive black holes in the center of the galaxy, and this really dense amount of dark matter could possibly self-annihilate and generate some gamma ray fluxes, and this could be observed by Fermi-Lat, for example, and other possible instruments. All right. So the idea is that when you have a spiral black hole that will go in the direction of the supermassive black hole, could be a black hole, could be a star, a neutron star, or something like that. It will emit a gravitational wave signal, and this will disrupt this cusp profile. And by changing the density, the density matter of the density of dark matter inside the galaxy, it will change the flux of gamma rays. That's the basic idea of the paper. I think that's very well, very good idea. So that's basically what I say in this third paragraph. Yeah, and that's the basic idea of the paper. Investigate the correlation between gravitational waves emitted by the binary black hole system and the reduction in the gamma ray emission from self-annihilating dark matter in dark matter spikes. That's the whole idea, the whole purpose of it. Sorry? Reduced, yes.
Why is that?
Because since we have some kind of spiraling, you will emit gravitational waves, and this is just like emitting energy from the system. Energy is coming out of the system in the form of gravitational waves. And this, like they claim, that will reduce the gamma ray fluxes.
So in this case, it would be harder to observe, for example, a complementary event of gamma rays in a gamma ray telescope, for example, and in interferometry.
Yeah.
But I don't get it, because the gamma ray signal has something to do with the dark matter annihilation.
Yeah.
The gamma ray signal has something to do with the spiraling of black holes. So different sources. So why one diminishes the other?
Basically, they say that I think that you will change the profile,
So
and
it should increase the
Yes, because you have more dark matter in the center of the galaxies if you peak the profile.
So the way we say it, like the primordial black holes accrete
Okay.
dark matter onto the black hole, right? Increasing the dark matter density and therefore increasing the flux, because the flux is proportional to the dark matter density, well, squared.
Okay.
So increase a lot, actually. And so I expect to have more gamma rays for the same reason that once you include once you include black holes into the picture, the constraints on the dark matter annihilation cross-section are much stronger. But since you expect lots of gamma rays and you don't see them, then your constraint is stronger. So the gamma ray, the limit input on gamma rays is like this. Let's say that Fermi or whatever has a limit on sigma v versus mass and goes like this. And let's say that here is, let's say, 3 × 10⁻26 centimeter cube per second. This limit is when you do not have upper limit, does not have black holes. Once you have more black holes, you have black holes accreting dark matter, so the density profile increases. There is a spike. Why spike? Because it's towards the center where you expect to have a primordial black hole, which is Sagittarius Ra. So you increase the flux, but I don't see it, so my constraint is stronger. And the way it goes, so let's say phi experimental limit is phi, let's say from background, plus flux from dark matter. Okay, these I measure. Supposedly I know this one. Okay. All right. So since I know this one, the only thing this is uncertain is this one. But then this thing I'm going to replace it by sigma v over m times m pi squared times rho squared. Okay?
Yeah.
So now think. Once I increase this ratio should be smaller. Once you include black holes, you increase this. If you increase this ratio should be smaller. Therefore, when you do include primordial black holes, when you increase this thing, this limit goes up here. So the sigma v over mass should be smaller to account for the same flux. So this is with black holes. So you expect more gamma rays, not less.
More or less. Yeah, they claim the opposite.
I think they will put some kind of dilution.
Exactly. They tell that these gravitational waves will emit some kind of energy out of the ceiling and will dilute the energy, the density profile, and as a consequence, they will have less flux of dark matter.
So they go in the opposite direction.
Okay, so you say that once you include black holes and those black holes merges emit gamma rays, you smear out.
Yes.
Yeah.
But the problem is because in the case you're treating, you have more black holes, but they are not spiked. They are not spinning around each other, or it's binary system. In this case, you have a black hole, a big black hole, right? So you should expect just accretion. But in this case, you can have emission of particles, like now Hawking radiation, and then you can have some kind of.
But how can you have just two primary black holes changing this?
But it's not.
They're not two primary.
Yeah. So how are you going to change with primary black holes or black holes changing?
I think it will change everything close to the center of this. Things, because they are spinning and they will merge. So it will make the particles go out. So the density will change. So you instead of expecting
the fluctuation is tiny, right?
It should not necessarily. It depends on the mass of the black holes. If it's supermassive black holes, so you expect a larger smearing.
But to change the density profile of the galaxy?
No, just in the closer.
In
not
the
in
vicinities
galaxy,
of the
just this
supermassive black hole.
Just in the small radius.
Yeah.
No values for the radius.
Okay.
Like I think they have seen something like this. For example, instead of you would have something like O R. So let's say you have something like this, but now you may have something like this, or where this would be the reference. The reference.
Flattens out the dark matter profile, right?
Yeah. It's I mean, it's I think my first impression, you really is we're gonna have more fluxes, but that is not what the dark matter, the black hole simulations that they make show us. Basically, there is this effect of dilute the density profile, and we have some kind. They consider two things basically. One thing will dark matter. Sorry.
So, in the moment they take a steeper profile, which is gamma equal 1.5. So okay. So rho is r proportional to r minus gamma. Gamma was 1, now it's 1.5. So it's over 4. And then yeah, I don't get it. But see, he's saying that he's considering the dark matter profile is goes like this.
Yeah.
So he's saying that the presence of these black holes, they make it the dark matter profile steep, is low. So the density profile was supposed to be like this. Minus gamma.
So there is a ratio of influence of the supermassive black holes.
Yeah. They
But it's not exactly Navajo.
Frankie White profile.
I know, but when he's focusing in the center, that's why he drops this term. Because in the very center, this term is neglected and it just is one dominates. So that's why this is proportional to rho r to minus gamma.
Yes.
That's what he's writing there. So for the Navajo, this is 1, right?
Yeah.
So let's do it like this. Rho over r. So let's say r being, let's say instead of 1, 0, because it cannot be 0, let's say 10 to minus 3. So this is like 10 to proportion to 10 to 3. Okay? Minus 1. So 10 to 3. Now if you put 0.5, this will be for the same r of 10 to minus 3, would be 10 to minus something. It would be much larger. So you're increasing the density. So if you increase the density, you expect more flux.
Yeah. I mean,
But then he's saying that for some reason the gravitational waves mirror out.
Yeah.
There are some kind of coupled equations.
They do not say a lot about what the equations they solve. They just say that they make some of the simulations with a code called Riga.
Because I know that, for
Is
example,
here?
when you have induced, because primordial black holes, for example, when they evaporate out, when they in the instantaneous decay process, they generate a kind of dilution. It comes from the induced gravitational waves perturbations, but in the scalar modes. So you're gonna have kind of a real dilution, let's say. So I expect that's the same. And since they are assuming there is a R of reference where the supermassive black hole.
I know, but yeah, okay, but remember, okay.
So perhaps it's like imagine something happens. There is gas, there is dark matter, but now something is spinning stronger because it's gravity which is playing. So everything we're gonna.
So they compute this?
Yeah, they make the simulations. Here, there's the.
They simulated, but
I mean,
there is no.
In this case, there is a very massive black hole, right?
A supermassive black hole in the center of the galaxy. Yeah.
What Jacinta is talking about is like Hawking radiation.
No, it's not Hawking radiation
No.
because Hawking radiation is properly radiation in the form of
Because the black holes
relative
stop,
particles.
they disappear, right?
Yeah, but because they have low mass, in this case, it's a massive black hole. The opposite.
For what?
For Hawking radiation, but it's not Hawking
No, not
radiation.
necessarily a black hole disappear by Hawking radiation, but in this case, it's just they are merging. And what I was talking about is about the induced gravitational waves produced by Hawking radiation, which is another phenomenon. But in this case, you have a merging, and I expected that when the supermassive black holes they merge, they will change the scenario. They will change what's going on around. You expect that there will be just a crashing, but I think it's not the case. You have something more nonlinear regimes. So
Yeah.
It's not real.
It's not trivial.
Yeah.
I'm always saying supermorph. There are two black holes. They are spinning. So they during the time they're spinning, they are creating dark matter.
But not only, they are also emitting gravitational.
But I don't
gravitational
know which
waves.
one of the two wins.
So the gravitational wave maybe make them to go up. They get some energy, for example.
Basically,
They go out. If, for example, dark matter couples to gravity, if the gravitational waves pass through this dark matter halo, that point, let's say, this particle will go out the region of escape. So they will escape instead of going inside.
and basically, we do not have two supermassive black holes. We have one supermassive black holes, and the other source.
It's like a target. It's a star.
Yeah. I mean, it's a
Companion.
yeah. It's a neutron star or some kind of. Sorry.
No, just the person.
I mean, no. They just say that it's a stellar mass complex object.
Is that paper? Okay.
So I mean, they say basically one of the important parameters are the mass of the black hole. Let me put this. The mass of the supermassive black holes. I mean, the small m is the mass of the companion black hole of the stellar mass object, and what is important is the binary mass ratio, Q. That's basically the ratio between the mass of the small object with the supermassive black holes. And I mean, they like Jacinto say, the spike densimal cusp is predicted to form inside this radio. It's a radio of a spike. There is it's 0.2 error h. This here is the radius of influence of the supermassive black holes. Basically, the radius containing contain a mass of 2m, 2 times the mass of the supermassive black hole. And they consider a cusp with this gamma here, with this gamma profile here, varying between 1.5 and 2.5.
One thing I should point out. So, for instance, Joseph Silk was the first one to point out that we could have a dark matter spike due to black holes. So that's why probably he's the co-author.
Yeah.
But it has been proven that you do not get a dark matter spike when you have a supermassive black hole. You don't.
He proved that.
No, someone else did.
Okay.
And that was confirmed by other groups.
Okay.
So the only way to get a dark matter spike is it would be if you had a population of intermediate massive black holes, a population across the galaxy,
Okay.
and they would accrete dark matter close to the center. Then all of them would accrete, and then If you have just one supermassive, you will not.
Yeah.
They have
He ignored anyways.
Okay. I mean, he
And he
said.
continued to write.
Yeah.
To write papers on this supermassive black hole.
Ah, okay. With this assumption. Okay.
He didn't care.
I don't know. He said here that there's the black holes grows adiabatically, and this will generate a spike. I don't know if this.
Check reference. You can click there. Click 7, reference 7.
7, yeah.
Okay, that's the no one. 7 or 17?
Pues 17, 7 y 17.
Seven.
717.
Scroll down.
See, there's one.
See there is one. Yeah, hasn't go up.
this is the
There was another one.
I think that was 35.
24 6. That's a recent paper. Okay, click on that one. The 17, just so we can check.
17.
Yeah, 17.
Oh, there's
go up.
question. This is the
Yeah,
one
click
from-
that one.
But this
Another-
is the
another
one
tab.
from the review. This is the review.
Oh.
Not matter.
I open.
Okay.
This is the not
Ah,
matter.
the review.
Okay.
But this is
Okay, continue this.
So, what they say is that they consider any body simulation, like I think that's each dark matter is considered a particle in this any-body simulation, and they model the response of the dark matter spike in the presence of this binary. I mean, this other black hole. And let me put here. I mean, this is basically the. I mean, I will pass first the what they made. Here is all the information, how they made this, how they put how they distribute the particle velocities along this profile, this dark matter profile. And what he considered is that a gravitational wave measure in time with 10 years, and he considered in his simulation that every dark matter particle within this 2 times the Schwarzschild radius will fall into the black hole. So he put out of the simulation all those particles that are inside this radius here, 2 times the Schwarzschild radius. Yeah, by the black hole. And another thing that he considered is that the other black hole or the other stellar mass object will spread some dark matter out of the system. So they are spiraling around the supermassive black hole and will some kind of scattering dark matter out of the system as well. So he considered these 2 types of dark matter. That's be eaten by the black hole and the ones that are scattered out of the system. And he do not. I mean, he just said that he used the code Rega, use Runge-Kutta order method. I mean, it's but he do not give all the details of what he solved. That's what I say. That's just a short letter version of a full paper. And basically, that's the any-body simulation. And here he make the connection with the flux of gamma rays. So basically, the connection is made by this astrophysical factor J here. That's giving 2 sources: the background source and the integral of the dark matter density over this region R max here, or that's the radius where the spike density drops to 0. So basically, I mean, he said that he can ignore this background and consider just the first part of the J factors. And he said that this simulation shows that he will kind of flatten this spike and will, because of that, the astrophysical factor J will decrease, and as a consequence, the flux will decrease. and he make this for different kinds of gamma factors. And here's the result. Gamma 0.5 is basically the almost constant. 1.5, I mean, you have a decrease in about little more than about 15%, and here 2.33. I think that's a special kind of cusp profile of supermassive black hole. I don't understand very well. This is just 7/3, and he'll decrease a lot of the flux. And here they make the same thing, but considering different mass ratios. Here just the first simulation with different gammas, and the other simulation with different mass ratios. And he showed that there's this decreasing on the flux. But I mean, I think that lacks some of the information of how they make the n-body simulation. They say, we make this n-body simulation, we use this code, this is the result. They lacks a lot of information of how, lacks a lot of the technical detail of how they make these n-body simulations, actually. And they consider basically, I mean, the mass ratio they consider and the time of spiral and mergers is just coincident with the frequencies observed by LISA. And here he just put a LISA sensitivity regime. This curve here is just the gamma ray flux. This here is the Fermi-Lat sensitivity, and the other here is the LISA sensitivity. So we can make, and we can study use the Fermi-Lat to observe this gamma ray or the absence of the gamma rays, and we can use LISA as well in order to put some bounds on the same gamma ray flux. I mean, I think that they say here in the paper that they should make a better discussion about. They just discuss here this very very rapidly. They do not discuss a lot of this about the sensitivity of this flux. They say that's going to do that in other papers. And the result, the conclusions here. Sorry. I mean, the basic conclusion is that this inspiral and merger will decrease the flux, something that can vary from 10% to 90%. And this could be observed in future observations. That's the conclusion. They say that they should consider more about the dark matter nature. They just consider, they do not consider here the nature of the dark matter itself, just that the spiraling and measure of the
That's funny because, for example, for the benchmark mass for the supermassive black hole that we choose, we have 10 to 6, 4 times 10 to 6 solar masses, but then the other mass is like 10 to minus 5. So it's almost, you have a sun. You have another sun, a sun, which is coming closer to the black hole.
Is there some kind of stellar mass?
There is no spin, exactly. I mean, you have just the star rotating and getting inside.
Yeah.
You don't have the proper spinning like I was expecting. Okay.
So that's the paper.
Could you please show the plot?
Yeah. Which plot? This one?
Now, the first ones, I wanted to check in detail, but...
This is the density profile. These are different trajectories, basically. And they all, I mean, we have...
What is it?
Let me... Yeah.
Okay.
Better? This curve here is the density profile in the beginning. And this other here is the density profile at the end, after the merger.
It's a function of the time of merger?
What is
There's
The distance.
Okay.
But what is the difference? Is there another difference between the panels in each column?
At different times.
Yeah.
No, okay. At different times, just the dashed and the solid. But,
These two here, right?
Yes, but what's the difference? Because in the second panel, for example, you have it's changed. It's the opposite. First, you have the spike for the beginning, then you have this. This is really this. So, but in the other case, you have the opposite. So, what is the difference between each panel?
This and this one,
To the caption.
the difference between these two
Yes.
is just the initial profile, if I'm not wrong. It's the gamma. Here's one type of gamma, here's another type of gamma.
Yes.
Here, there's one is the 0.5 and the other, the right is 7/3. That's the 2.33. That's it.
So in this case, this difference would also change according to the spike, to the index spectrum.
Yeah.
Spectrum index. Okay, well,
That's the result.
Alright,
last page.
How can I leave here too?
So one thing that I was thinking is about the beginning of April. So I was thinking of giving maybe 2 or 3 lectures on an introduction to dark matter, especially because of them. What do you think?
We'll do that.